Hello, my name is Dr. Ian McNeil. I am an assistant professor in the chemistry department, also an alum of Bridgewater College, class of 2008. And today I'm working with the Office of Alumni Relations, and I am going to talk about my research on characterizing dye-sensitized solar cells, or in other words, we're going to learn how to make a solar cell out of whiteout and raspberry juice. So right now I'm going to talk a little bit about the theory of how it works, and then we'll actually head into the lab and we'll actually make a device to see how it works. So first off, the theory. The first thing we're going to talk about is to understand how solar cells work, we have to have an understanding of what semiconductors are. So if I have a single atom, your electron is going to exist on the atomic orbitals, and you'll have your ground state and your excited state. If you bring your two atoms together to form a molecule, you'll form molecular orbitals. And here we're going to have our collection of our HOMO, the highest occupied molecular orbital, and you'll have your excited state, which will be the collection of the LUMOs, the lowest unoccupied molecular orbital. So if you have one atom, you have the ground state and the excited state. If you bring two atoms together, you'll have two molecular orbitals, meaning you'll have two ground states, two excited states. If I bring three atoms together, three ground states, three excited states, bring four together. And at this point, you can kind of see I have this band of ground states and this band of excited states. So we have special names for these different bands of energy states. This band of the highest occupied molecular orbitals is called my valence band. And this band up here is going to be called my conduction band. So here, electrons are kind of bound to a specific atom. Here, electrons can flow throughout the material. That's why it's called the conduction band. It conducts electricity. So to understand semiconductors, we're going to compare it to metals and insulators. So here in a metal, our conduction band and valence band actually overlap. So even at room temperature, you could have electrons that can exist in your conduction band, and so metals are really good at conducting electricity. With a semiconductor, there's a small energy gap between our valence band and our conduction band. So with a little bit of energy, we can actually excite an electron from our valence band to our conduction band. And this energy gap is called the band gap. We'll talk more about that in a second. With an insulator, there's a huge energy gap between our valence band and our conduction band. And so it takes an enormous amount of energy. So for the most part, these materials aren't going to conduct electrons. So this would be something like wood or plastic. This is why we wrap our metal wires with an insulator, because they don't conduct electricity very well. But we are going to use semiconductors for our solar cells because it takes a little bit of energy to excite an electron from our valence band to our conduction band. So this is a little cartoon about how solar panels work. So we have the solar panel that you're used to. We have our sunlight. Here we have our electrons residing in our highest occupied molecular orbital. So right now it's occupied. So whenever sunlight hits the solar panel, that light is absorbed by the electrons and it excites an electron into the conduction band. Then I can use it through my load to power up my electronics. That's kind of the idea of how the solar panels work. So the solar panels that you often think about are made of crystalline silicon. So why do we use silicon? So one thing is that it's really abundant. If you go to the beach, sand is silicon oxide. Silicon very abundant on the Earth's crust. That's one reason. But the other reason has to do with this band gap. So the energy spacing between the valence band and the conduction band is 1.1 electron volts. So if you aren't familiar with your units of energy, that's okay. There's this equation right here that relates the wavelength of light and the energy. And if you put this value in as your energy and do your algebra, you realize that this corresponds to a wavelength of 1,127 nanometers. So what does that mean? So I need light that has an energy of at least 1.1 electron volts, or in other words, I can say a photon with a wavelength of 1,127 nanometers or shorter, because remember, the higher your energy, the lower your wavelength. So lower wavelengths equal higher energy. So as long as I have this energy and greater, or this wavelength and shorter, I'll be able to excite an electron from my valence band to my conduction band. So let's compare this to the solar spectrum. So right here I have the different wavelengths, and here I have the spectral irradiance. So basically, how many photons of each wavelength is emitted by the sun. And if we treat the sun like a black body radiator, this is what this black curve right here is, we can predict what wavelengths will be emitted. And so this model is pretty good at predicting what wavelengths are emitted by the sun. And then the yellow and the red is actually what we see, we measure. So the yellow is the number of photons from each wavelength that actually hit the outer atmosphere of the Earth. The red is what actually makes it to the surface of the Earth, because some things in the atmosphere, like water and carbon dioxide, are going to absorb some of those photons. So the red is what color of light actually makes it to the Earth's surface. And this line right here represents that wavelength of light that we need, or the wavelength or shorter that silicon has to absorb sunlight. So silicon can absorb at this wavelength and less than. So you can see most of the solar spectrum is actually absorbed by silicon, which is what we want. All right, so what are some problems with silicon? Well, it's very abundant. As I said, if you go to the beach, lots of silicon. But in order to use it as a solar panel, you have to have very, very pure crystalline silicon, like 99.9999 plus percent. So purifying the silicon to be this pure is very, very expensive. Also, the band gap is small, which limits how much energy we can actually get out of the device. So to understand what's going on there is if I have my valence band and my conduction band, and I come in with low energy red light, so just enough energy to excite an electron into the conduction band, I can do that. Great. Now let's say I come in with higher energy blue light. I would like to be able to use that extra energy because I'm absorbing that extra energy. I'd like to be able to use it. But what happens is I excite an electron to an upper level excited state, but then it's just going to vibrationally relax, give off energy as heat, and go back to the same conduction band energy level as it was before. So I didn't gain any energy. So it has a fairly small band gap, so it kind of limits how much energy I can actually get out of my device. So I want something that's cheap, and I want something that has a large band gap. So one solution is called titanium dioxide, or TiO2. TiO2 is very cheap and abundant. It's used as a white pigment. So I've seen it listed as ingredients in toothpaste. It's probably the pigment on the white paint of the walls right now. I've actually seen it listed as an ingredient in the white powdered donuts that you get. It's what makes the powdered donuts like bright, dazzling white. And it also is an ingredient in sunscreen because it absorbs the sun's energy. It's a wide band gap material, so electrons will have more energy because its band gap is 3.2 electron volts compared to the 1.1 electron volts of silicon. So this band gap corresponds to a wavelength of 387 nanometers. So let's go back to the solar spectrum. So here's our solar spectrum, and here's where silicon lies. So TiO2 lies right here. So you may be able to start seeing kind of the problems with TiO2. So silicon can absorb all of these wavelengths, but TiO2 can only absorb a little bit. Now, it can absorb UV, it's used in sunscreen, but UV is only a small fraction of the light that's emitted by the sun. So how are we going to fix that? So the way we're going to do that, it's called sensitization. So what we do is we have the valence band and the conduction band of TiO2, and on the surface of our TiO2, we're going to chemically bind a dye molecule. So a dye molecule is just a molecule that has color. It absorbs specific wavelengths of light from the sun. And I have to design my dye molecule carefully so that I want the energy spacing between the ground state and the excited state of my dye to be smaller than that of the band gap of my semiconductor so that it can absorb lower energy light, because I want to absorb more of this red, lower energy light. But my excited state has to lie energetically above the energy of the conduction band. So what can happen is if my dye molecule absorbs light from the sun, it will excite an electron to the excited state of the dye molecule, and then through a process called either electron transfer or electron injection, I'll transfer an electron into the conduction band, and now that electron can be used for electricity. So I was able to absorb light of lower energy, but still create an electron that has enough energy to be able to use for your electronics. Right, so we're going to incorporate a dye-sensitized solar cell. So a problem, though, is if you just have a smooth layer of your TiO2, you only have one atom layer of dye molecules to absorb sunlight, which isn't going to absorb that much light. So what we're going to do is we're going to create this nanoparticle film with lots of nooks and crannies where that increases the surface area, lots of space to put those dye molecules. We can absorb a lot more sunlight that way. So we're going to create this nanoparticle film of TiO2 and sensitize it with our dye. So here's a cartoon of a complete dye-sensitized solar cell. So we have our light coming through our transparent electrode. We have our TiO2 nanoparticle film that's sensitized with the dye molecule. So I'm going to kind of walk you through the whole cycle. So light comes in, it excites an electron from the ground state to the excited state of the dye. The dye then, the electron undergoes electron transfer into the semiconductor. The electron then diffuses through this nanoparticle network, goes to the electrode, goes to the load to power your electronics, goes to the counter electrode, and then over here, between the nanoparticle film and your counter electrode, you're going to have an electrolyte solution that allows your electrons to be kind of shuttled through the device. So here at this interface, so our electrolyte solution contains iodide and triiodide. So at this interface, the iodide is reduced to become triiodide. Then triiodide can diffuse through your device back to the dye, and then it is going to reduce the previously oxidized dye molecule. Your electron goes back to the ground state. You can repeat that process over and over again. In grad school, whenever I was learning about this process, we were using these inorganic dyes that had a ruthenium center. So these inorganic dyes are very stable. They have a long lifetime, and they're very efficient. So they absorb around 630 nanometers, so they have this bright orange color. They have a long-lived excited state, so that means that once they are excited, they're excited for 100 nanoseconds to 1 microsecond. So you have a long time. This seems like very, very quick, but in the grand scheme of things of the life of the electron, this is a very long time. And you have a very long time for that electron to be transferred to the TiO2. And the excited state of this dye molecule is above the TiO2 conduction band. So if you're looking at current research in dye-sensitized solar cells, you're often going to find these ruthenium inorganic dyes. However, in the interest of green chemistry, where we're trying to not use these kind of rare inorganic metals, we're looking for more natural dyes. So for our research, we are going to use a dye molecule called anthocyanin that's found in raspberry juice. So instead of this bright orange, our devices have this purple color that come from this anthocyanin dye. So we sensitize our devices with raspberry juice, and our research is looking at these devices, characterizing their performance and kind of understanding all of the different kinetic processes involved in this to make them more efficient so that we can actually get these out there and compete with the traditional solar panels that you think of when you think of a solar panel. So with that, I just want to take some time to thank my previous research students in my lab. All these students have worked with me in the past and helped me get my research off the ground here at Bridgewater, and we've presented posters at numerous conferences across the country, and just recently we have had a paper accepted to be published in the Journal of Solar Energy, so keep an eye out for that soon. And at that, we'll head to the lab and I'll show you how to make a device. All right, so now in the lab, we're actually going to go through the process of making one of my dye-sensitized solar cells and see how it works. So the first thing we do is we create this little TiO2 paste. This would look just like what you would think if you opened up your bottle of whiteout. It's just a paste of white goop. And then what we do is we apply this paste onto this conductive glass, and then we have these little stencils and we smooth it out. And this is where I want to support diversity in STEM, because we were having issues with applying a nice thin coating of this film, and one of my research students recommended using a makeup brush. And I would have never have thought of that. And so I encourage the diversity in STEM because the different perspectives allow us to progress science even further. So yay for diversity. So we smooth out the film onto these conductive glass slides, let it air dry, and then we bake them overnight in an oven downstairs. So this is a film that I already pre-baked, and so it looks the same thing. It's just this white TiO2 film, and now we're going to sensitize it with our raspberry juice. So we've already have this collection of raspberry juice that's actually right here, and we just pipette a small amount of raspberry juice, so it has this pink color. That's the anthocyanin dye. We pipette it on our film and let it soak for about 10 to 15 minutes. So after about 10 minutes of soaking under the raspberry dye, and I just soaked it off with some methanol, you get this film that has this purple tint. So that's how you know that our film is sensitized with the raspberry dye. So now this is our working electrode. For our counter electrode, what we do is we are going to use carbon soot from a candle. So I just simply light this. Oh, before I do that, I got to figure out which side is conductive. So our glass slides, these are FTO glass slides. These are fluorine tin doped oxide. So they have a small layer of tin oxide doped with fluorine, and that's what makes them conductive. So I got to make sure I know which side is conductive. So I use my multimeter to see which side has low resistance. So this side has low resistance, so that's our conductive side. So that's the side I'm going to put the counter electrode on. Yes. Light my candle. And I'm just going to run my conductive side with the conductive side down over the flame, and that's going to collect a film of carbon on my conductive slide. So you can already see it, how it's forming a layer of carbon soot on my conductive slide. So this is a conductive side I made earlier where I've already created the carbon layer, and then I wiped off enough to match the area of my working electrode. So now that I have my two electrodes, I'm going to take my electrolyte solution. This is the iodide triiodide solution. And here, this solution also contains lithium perchlorate. So lithium has been shown to increase the efficiency of the device performance. So we're going to add that to hopefully get a better performing device. So I put just 3 drops of my electrolyte solution on. I sandwich it over the top, and then I clamp it using these little clips. And now I have, hopefully, a working device. Right, so we've connected up our finished device up to our multimeter, and we're going to test to see if it's photoreactive. And so here we have a little lamp. We're going to put it on top of the device and look to see if we're going to be measuring voltage. We're going to see if the voltage increases. So right now it's not at 0 because there are some lights on in the room, but when I put the light onto the device, we see that the voltage does in fact increase. If we move the light off, the voltage decreases. So our device is definitely functioning, and it is photoreactive. Yay! So I hope you enjoyed learning about my research on dye-sensitized solar cells today. Hope you learned something. And if you have more questions, I hope that by next homecoming we can actually meet face-to-face closer than 6 feet away, and I can tell you more about them. Thanks. Bye.